Well, in previous lecture we discussed about Newton's method for solving nonlinear equations. On this slide you can see the main formula of the Newton method. We consider some numerical examples how to find the square root of 2 or square root of 17 using this approach. We consider some graphical interpretation. We discussed that the geometric interpretation of the derivative is a slope of the tangent line, and in this case we can consider Newton method as follows. We have a point xm, we have a tangent line, and we select the next point, xn plus 1, as a point of intersection of this tangent line and the real line x. And after that, the Newton method repeats. This method is very easy to implement using any programming language. I ask you to write the program that implements Newton method. I don't know, did you solve this task or not? I'm sure that you didn't solve it. Let's consider some example. Or it's not the Euler method. So Newton method, of course. Not Euler method, but Newton method. I open another solution. Let me open now another solution, Newton method. Well, what we should write to solve the equation? Suppose our goal is to solve the equation x minus cosine x equals to 0. Our goal is to find such x that x equals to cosine x. To solve this equation using Newton method, we should declare the function f of x like this, and we should write the function of derivative df. In this case, the derivative will be 1 plus sinus x. This is the derivative. And after that, the Newton method can be implemented as follows. The initial point, the first point x1. We use only 2 points. x0 can be considered as a current point and x1 can be considered as a next point. Then we ask about the number of steps and the tolerance. And this is the main loop of Newton method. This loop is more or less correspond to this pseudocode that you may find in my presentation. While module x1 minus x0 greater than tolerance and the number of steps smaller than n, we repeat the following actions. Let's store the previous values of x1 in the variable x0 and update x1. We update x1 using Newton's method. X minus f of x over f prime x. x0 minus f of x0 over gf of x0. And that's all. This is the main line and this is the main loop. After that we increase the counter, and if at the end of the loop the number of steps equals to n, in this case it means that the method failed to solve the problem after n iterations. Other case, the method solves the problem and the solution is x1. Let's run this method. First, we should input the number of steps. Wait a second while the program is compiling. Number of steps, for example, 10. The tolerance, for example, 10 power minus 6. And it's enough to carry out just 4 iterations to obtain the solution with this tolerance, 10 power minus 6. Suppose that we increase the tolerance. Increase means decrease. So suppose that what happens? Some problem with Visual Studio. Let me run it again. Number of steps 10, input tolerance 10 power minus 10. 5 iterations, it's enough to solve the problem. Number of steps 10 and input tolerance 10 power minus 14. Again, just 5 iterations. But if the number of steps is 2 and tolerance is power minus 10 power minus 14, 2 iterations is not enough to solve the problem. The method failed to solve the problem with tolerance 10 power minus 14. Again, one student connect to our meeting as a guest. Please reconnect to this meeting and input your real name, because I cannot fix your attendance as far as you log in just as guest. if we need to change the function, we can do it. This is another example. The function is x minus 2 power minus x. The derivative of this function is 1 plus 2 power minus x times log 2. And we can run the method again for another function. Number of steps is 10 power minus 6, and again it's enough just to carry out just 4 iterations to solve the problem. This is a solution. As you see, the Newton method is very fast, and it can be proved. It can be proved that this method is very fast. Let's carry out some error analysis. Let me remind you, but by error we mean the quantities En that equals to xn minus r. R is the real value of root. Xn is our approximation. The difference between r and xn is error that we get on a step number n. If we assume that the second derivative of a function is continuous and r is the root of the equation, f of x equals to 0, then from the definition of the Newton method, we have the following equation. En plus 1 equals to x n plus 1 minus r, that equals to xn minus f of xn over f prime of xn minus r, that equals to En minus f of xn over f prime of xn. And finally, we can write it as in the form En times f prime of xn minus f of xn over f prime of xn. By the Taylor's theorem, we have that f of r equals to 0 from the one hand, because r is a root, and from the other hand, it equals to f of xn minus En, that we can write as f of xn minus En f prime of xn. Actually, these two terms are written here, and we can write that this difference equals to 1 over 2 En squared times second derivative at the point xn, where xn is a sum point between xn and r. And finally, we have that the error on the next step. It means en plus 1 equals to some constant times en squared. This equation tells us that the error of the method on the next step, en plus 1, is roughly a constant times en squared. This desirable state of affairs is called quadratic convergence. It means that the precision of the real solution is doubling with each iteration of Newton's method. If at the current step we have some error smaller than 1, then on the next step the value of the error will be en squared. The precision is doubling. Well, we consider the theoretical properties of Newton's method. I show you the solution, the program that implements Newton method. And now let's switch to the last topic that related with the nonlinear equation, fixed point iteration method. First, let's consider some definitions. A number p is called a fixed point for a given function if g of p equals to p. So the property is very simple. P is called a fixed point if g of p equals to p. This is a property of a fixed point. And a root finding problem and a fixed point problem are equivalent class of problems in the following sense. If we have a root finding problem, this is that if we have an equation f of x equals to 0, the equation, we can define auxiliary function g of x, g of x equals to x minus f of x, and if g of x has a fixed point at the point p, it means that p equals to g of p. It means that f of x has a root at the point p. F of p equals to 0. So we can reformulate these problems. If we have a root finding problem, we can formulate a fixed point problem based on this one. and vice versa. If we have a fixed point problem, we can reformulate it as a root finding problem, and so on. From the graphical point of view, the fixed points are the points of intersection of a line y equals to x, this line, and the graph of a function. If we consider the function y of x equals to x squared minus 2, this is the graph of this function. In this case, I can say that this function has two fixed points. P1 equals to and P2 equals to minus 1. These are two fixed points, the points of intersection between the line and the graph of a function. How to reformulate it as a fixed point problem is very simple. We can write f of x equals to x squared minus 2 minus x, and f of x equals to y of x minus x. But we can ask a question. Does this function have a fixed point or not? The following theorem gives sufficient conditions for the existence and uniqueness of a fixed point. This is the formulation of this theorem. If the function g of x is continuous and the values of this function g of x belongs to the interval from a to b for all x from a to b, then g of x has a fixed point between a and b. So it means that the graph of the function lies somewhere here inside this square between a and b and a and b. It means that here, in this case, it must be a fixed point. But if, in addition, the first derivative of the function g exists and a positive constant smaller than 1 exists, such that module g of x, g prime of x, smaller or equals k for all x, then this fixed point is unique. Means that there is only one fixed point. So I repeat again, if the function lies somewhere here inside this square, and if the derivative of this function smaller than k, where k is smaller than 1, then the fixed point is unique. Here you may find the proof, but it's if you are interested in, you can read it from my presentation, but now I skip this proof. You can read it. Let's consider the example of this theorem. The question is, does the function g of x equals to x squared minus 1 over 2 have a unique fixed point in the interval from -1 to 1? Let me now switch to the board. I stop sharing the screen and I want to write the answer of this question on the board. What should we do? First, we should answer the question: what are the values of the function? The function g of x equals to x squared minus 1 over 2, and x is from -1 to 1. If we look to this function, and if we look to this interval, we can decide that the values of the function is also from -1 to 1. Sorry, I should. Okay, let's continue. Well, if you look to this function and if we look to this interval, we can decide that g of x is also the values of g of x will be also from -1 to 1. This is the first statement of the theorem, and if it's true, we can say that this function has a fixed point. And the second property, we should find the derivative of this function, g prime x. G prime of x equals to x, and on the interval between 0 and 1, it will be smaller or equals to 1. The module of a derivative will be smaller or equals to 1. That's why we can say that the second property of the theorem is also true, and this function will have the fixed point on the interval from -1 to 1. Now I share my screen again. We consider the properties of fixed points, and now let's discuss about the method. How to find a fixed point by function of a function numerically. To approximate the fixed point, we choose an initial approximation p0 and generate the sequence Pn by letting Pn equals to g of Pn minus 1 for each n greater than 1. So the method is extremely simple. Just take the current point and compute the next point Pn as g of Pn minus 1. If this sequence converges to P and g of x is continuous, then P equals to limit of Pn that equals to limit of g of Pn minus 1 that equals to g of limit Pn minus 1 and that equals to g of P. And a solution to x equals to g of x is obtained. This technique is called fixed point iteration. This method is very flexible and can be applied for solving wide class of problems. In particular case, the problems of solving for finding the roots of equations. On this slide, you can see the pseudocode of the algorithm that implements fixed point iteration. As in previous case, this algorithm has three input parameters: the initial approximation P0, the reasonable tolerance, and the maximum number of iterations. The output of the algorithm is a solution P or the message of fail. And the main loop is written here. While I smaller than n and P minus P0 greater than tolerance, then we do two main steps. We update the value of P0 and we compute the new value of P as g of P0. And after that, we increase the count. When the loop is finished, and if the number of steps equals to n, then the method is failed. Other case, the procedure was successful. Later I will show you the implementation of this method in C++. But now I show you the two examples, two graphical illustrations. Suppose that this is a graph of the function g of x, and this is a line y equals to x. How the method works? First, we select P0. After that, we take this value and compute g of P0. This point we consider as P1. Then we select P1 and compute P2 as g of P1. Then we can select P2 and compute g of P2, P3, and so on. So the method works, this trajectory looks like a spiral that converges to this point, the point of intersection between this function and this line. And we become closer and closer to the real solution. This is one situation, and this is another situation. Suppose that this is a function, and this is a real line y equals to x. We select the point P0. We take it as the first point. We compute the value P1 that equals to f of g of P0. Then we compute P2, g of P1. Then we compute P3 as g of P2, and so on. And the method generates a point that moves closer and closer to this point of intersection. But the graph of movement looks like a stairs that converge to this point. But in any case, in this case or in this case, we have a convergence to the real solution. Well, to understand how the method works, I ask you to do the following. Okay, let's write the example from the previous. Let's take this example, x minus cosine x. So let's consider f of x equals to x minus cosine x. And I ask you to compute first 2 points using the fixed point iteration method. So the main idea is, and the main formula is written here. This is a pseudocode of the algorithm. I ask you to consider the function x equals to x minus cos x. For example, let's select x 0 equals to 0. And I ask you to compute x1 and x2. So the task is apply a fixed point method, fixed point iteration method, and compute x1 and x2. Please do it now, and after that tell me your solutions. You have this presentation. I will send it you a few weeks ago. You have it. If you don't understand the topics in my presentation, just type fixed point iteration method in Google, and the first link will follow you to the Wikipedia, and you can find more or less the same examples. Please look to this picture. This picture is more or less that I show you in my presentation. And this spiral also, yeah? This spiral more or less the same as in my presentation. You can find a lot of material about fixed point method. Please do it, compute these 2 points. And you have 20 minutes to do it. After 20 minutes, you will have a break. And after that, we continue the lesson. We discuss about your solutions and we consider the correct solution of this problem. You have 20 minutes to solve this task. I come here, and after that we discuss about your solutions. Well, did you solve the problem? Can you show me your solutions? Well, how to solve it? First, we should reformulate this problem as a fixed-point problem. It's very simple to do. G of x equals to x minus f of x. G of x equals to cosine x. And after that, according to the formula, P equals to G of P, or I can say that x n plus 1 equals to G of x n. We can compute the points. The first point, x0 equals to 0, x1 equals to G of x0 equals to cosine x0 equals to 1. Cosine, because cosine 0 equals to 1. x2 equals to G of x1 and equals to cosine 1, cos 1, and so on. Step by step. After that, we can compute x3, x4, and so on. And we find the solution of the fixed point problem. I can show you the implementation of this method. Let's look to the Visual Studio and problem. What is the problem? The problem is x minus cosine x to 0. This is the problem. What is the function g of x? Function g of x equals to cosine x. That's all. This is our main point. After that, we should declare the necessary variables, for example, the variable P0 and P, the tolerance, the number of steps, and implement the method following these pseudocode. While these two inequalities are true, while I smaller than n and FAP's absolute value of P0 minus P greater than tolerance, then we update the point P and compute new point P equals to G of P0 and so on. And we finish. If n equals to I, it means that the method failed to solve the problem after n iterations. Other case, the solution is correct. Let's run this problem, and we will see that the approximate solution to this problem is 0.7380, and we find it after 35 iterations. If we check that g of x equals to x, it's true. Let's take not 10 power minus 6, but 10 power minus 3. You see that the tolerance is 10 power minus 3. The number of iterations significantly reduced, not 35, but only 18 iterations. And here you may see that g of x, 739 equals to 738, because, if you remember, I assign a tolerance 10 power minus 3. If I put here 10 power minus 10, the number of iterations increasing, 59 iterations, and g of x equals to x. If you remember, when we apply a Newton method for solving the same problem, let's apply a Newton method. And let's take the same And when we run a Newton method for the same tolerance, 1e minus 10, it's enough just to have 5 iterations. When we solve it by fixed point iteration, is 59 iterations. You see that the Newton method is significantly faster, 10 times faster than fixed point iteration method. Why? But the Newton method used first derivative, and the fixed point doesn't use the first derivative. Fixed point method used only a function value, g of x. But when we apply a Newton method, we should compute a function and a derivative of a function. But if we don't know the derivative, we cannot apply this powerful method. Well, so again, this is an implementation of a fixed point iteration method. This implementation corresponds to this pseudocode. And now in the finish of this lesson, let me show you some theoretical properties. Some theoretical properties of the method. These theoretical properties are formulated in a form of the following theorem and corollary. I show you these statements without proof, just a formulation of these statements. The theorem: if the function g of x is continuous, and if g of x belongs to the interval from a to b for all x between a and b, and in addition g prime of x exists, and a constant between 1, 0 and 1 exists, such that g prime of x smaller than k for all x between a and b, then for any number p0 between a and b, the sequence defined by the following formula: Pn equals to g of Pn minus 1 converges to unique fixed point P between A and B. So if these properties are true, then the fixed point method converges to unique fixed point. And the corollary from this theorem tells us that if g of x satisfies the hypothesis of the theorem, then the bounds for the error involved in using Pn to approximate P are given by the following inequalities: module Pn minus P smaller or equals k power n times maximum P0 minus a B minus P0, and Pn minus P smaller or equals P1 minus P0 times k power n over 1 minus k. These two inequalities gives us the bound for the error. I skip the proof of the theorem, and also I skip the proof of the corollary. Let's discuss about this formula that follows from the corollary of the theorem. P minus Pn smaller or equals k power n over 1 minus k P1 minus P0. Both inequalities in the corollary relate the rate at which Pn converges to the bound k of the first derivative. And here, the rate of convergence depends on the factor k power n. Let's look to this inequality. In the left-hand side, we see the error, the absolute error at the step n, P minus Pn. And In the right-hand side of this inequality, we see the initial pair P1 minus P0, the difference between first two points, and some factor that depends on k. K power n over 1 minus k. K is a bound of the first derivative. K is the upper bound of the first derivative of the function g of x. The smaller value of k, the faster the convergence. Suppose that k equals to 0.1. Then k in square equals to, if k equals to 0.1, suppose that k equals to 0.1, in this case k power 2 equals to 0.01, k power 3 equals to 0.001, and so on. This term becomes smaller, smaller, and smaller at every step of the method. And the convergence will be fast. But in the case when k is large, k must be smaller than 1, but it can be close to 1. Smaller than 1, but close. For example, it can be 0.9. If k is 0.9, then k squared equals to 0.81, k power 3 equals to 0.72 something, and so on. The method converges, but the convergence is slow. And if k will be close to 1, the convergence may be very slow. You see it on this example, that here convergence is slow. We have 59 iterations, but let's consider another function, cos x over 2. The equation x minus cosine x over 2 equals to 0. In this case, the derivative of this function will be smaller, 2 times smaller. Let's run the method and let's compare the number of iterations that required to solve it. You see that 17 iterations. We take the derivative 2 times smaller, and convergence becomes significantly faster. Suppose that we take not 2 times smaller, but 10 times smaller. Just 7 iterations. Very fast convergence. But if we take not 2 times smaller, but for example, just 3 over 4. Okay? 3 over 4 is smaller than 1, but is larger than just 1 over 2. "29 iterations. convergence becomes rather slow. But just for cosine, 59 iterations. What happens if we take 2 times cos? The method failed to solve. I can say that the method diverges because for the problem x equals to 2 times cosine x, the conditions of the theorem are failed, and the method failed to solve this problem. Well, let's come back again to this presentation and let's consider the final example. Example 1. For g of x equals to x minus x cubed minus 4x squared plus 10, we have that g of 1 and g of 1 equals to 6 and g of 2 equals to minus 12. So g of x doesn't map the interval 1, 2 into itself. Moreover, the derivative of the function g of x, g prime of x equals to 1 minus 3x squared minus 8x is greater than 1. So there is no reason to expect the convergence of the method for this function. Let's consider another function. For example, g of x equals to 10 over 4 plus x power 0.5. For this function, we have for all x in the interval 1 to x that module g prime x equals to minus 5 over square root of 10, 4 plus x power 3 over 2 is smaller than 5 over square root of 10 times 5 power 3 over 2, that is smaller than 0.15. It means that the upper bound of the module of the first derivative is 0.115. The bound for the magnitude of the first derivative is small. And we can expect the rapid convergence of the method if we try to solve fixed point problem for this function. Well, the task to you, try to write a program that implements a fixed point method. I already show you, but try to do it itself. Try to do it by yourself. Try to write a program, find the solution, with a tolerance 10 power minus 4, and compare the theoretical estimate to the number of iterations actually needed to solve this problem. G of x equals to pi plus 0.5 sinus x over 2. This function should have a unique fixed point on the interval from 0 to 2π. Well, this is a task for you for the next lesson. This presentation I already sent it. The program, the examples how it can be written, I already show you for you. Well, there are 3 students now here. If you don't have any questions, let's finish our lesson. Next week we will start the next topic. Interpolation. According to our schedule, we start the next topic, interpolation. If you don't have any questions, let's finish our lesson. Later today I will send you the video file with this lesson. Next week we will have 1 lesson. Please don't be late. Connect to our lesson in time. And the students who are here in Russia, they must come to this room and to be here physically. That's all. Goodbye.